So curvature and normal vectors of a curve. Curvature of a curve is k, or I think kappa technically is what's used for it, but regardless. And the principal unit normal vector is the vector n equals the derivative of the unit vector, the tangential unit vector, divided by the magnitude of that. Same vector. Same derivative of vector. And then, of course, t is equal to v divided by magnitude of v. These are just the formulas used in this exercises, really. Yeah, basically the first two problems, 1 and 3, we're going to do we're going to find just these three properties, three different values, things. Two vectors in the curvature would have given plane curves, and these are plane curves that are in essentially just in 2 dimensions as far as I can tell. That's why it's called plane. 2 variables. So RT equals TI plus the natural log of cosine TJ minus, that's it, and it's between those two values. There's a reason it has to be less than and not less than or equal to, or something like that, is because, well, it matters t, even though we're not finding anything with no integral or anything for this. There's a reason for it. Sine and cosine are fine. If we have sine and cosine, those are okay for any term. If we bring a tangent function into it, or maybe even a secant function, which if you look ahead you can tell, if we put those into it, then they're undefined at pi halves and negative pi halves when you equal it, but if you don't equal it, then you're fine. Like if it's just below it, right below it, then it'll be fine. Or right above it, So that's why it just has to be specified, pretty much. Or else, if it includes that point, if let's say t could be anything, it would have these discontinuous points, and if it's not continuous at all points, then you can't technically do it. Derivatives and a derivative has to be of a continuous function, pretty much, as you know, or integral the same way. You have to have it be continuous. So we could not do this kind of stuff if we don't have that specified domain. Regardless, and that's what happens. See you later, but. I haven't mentioned it one more time to make sure you understand. So we have that position function, and the derivative is just I for the I component because it's t. Derivative of t is 1, and the natural log derivative. What's the natural log itself is in the denominator. Numerator is the derivative of what you're taking the natural log of. So cosine t's derivative is negative sine t. Cosine t is the original function. Okay, that's either a calc 1, end of calc 1 or early calc 2 concept. Rush to the natural log derivative when you have a case like that. So it's I minus sine t cosine tj basically. Oh, but this is also can be simplified down to tangent t. So it's I minus tangent tj. Then the magnitude is 1 squared plus negative tangent t squared, and so it's 1 plus tangent squared t. And this is equal to the square root of secant squared t, which is equal to secant of t. Very simple. The reason is, and we're going to be looking at some trig stuff kind of again, like these trig functions, they never leave you, no matter what. I mean, you can try to get away from them, but you can't hide from trig functions. None can hide from a trig function, especially when you're a mathematician or even an engineer. But, okay, so sine squared t plus cosine squared t equals 1. We know this. I've told you that it's a common fact, easy to memorize out of all these. It's the easiest one to memorize, I'd say, out of all these relationships. Because it seems simple. You divide by one of the other function, by let's say cosine squared t. You get tangent squared t is sine squared divided by cosine squared. And cosine squared divided by cosine squared will be 1. So tangent squared t plus 1 is equal to 1 over cosine squared t, that's equal to secant squared t, because 1 over cosine is equivalent to secant. 1 divided by cosine. So 1 divided by cosine squared t will be secant squared t, and you can check, you could check this with values on a calculator, multiple values, and see what happens. Or try to graph it on a calculator to different functions and see the equivalence. Point is that we have that relationship, and that's what we used. Yeah, so the magnitude of vector is secant t, and for those values t. And now it's time for us to finally solve our three components now that we have what we need. Well, the first component t we can solve. So just division here like before. Oh, but we're going to simplify it down because we're going to have to take a derivative of this. We especially want it to be simplified because we want to make our derivative easy. When we take the derivative of the, tangential unit vector, whatever it's called exactly. And these vectors all blur together. Names of them. No, but the vector of capital T. 1 over secant ti minus tangent t divided by secant t. Okay. So 1 divided by secant t is equivalent to 1 divided by cosine t, as I said before, and that'll just be cosine ti. Makes sense. You basically do 1 times cosine t over 1 because you just swap the numerator and denominator and multiply reciprocal. Same thing with this. So tangent t is sine t, is cosine t divided by secant t, so that's multiplied by 1 divided by 1 cosine t. And it's 1 divided by it because it's in the denominator. So multiplying by it it can be 1 times 1 over secant t, which is secant t is 1. Point is that, and without getting technical, it would be times just cosine, basically. Cosine over 1. Yeah, like in that. But also I just cancel it out like that. So basically it's obvious that negative sine t is what your j value will be. J. So, and the derivative is simply put very simple here. I'm saying now, it's negative sine ti minus cosine t, because those are derivatives of trig functions. Then the magnitude of it, since we need it now, ends up with 1. We've seen this a couple times, especially in this simpler form. You're doing cosine squared plus sine squared. Yeah, you're going to get 1. And the square root of 1 is 1. Division, so n is the same basically, well, it's the same as just the derivative of t with respect to little t, because it's divided by 1. Oh yeah. That's your n vector. The principal unit normal vector, we're going to call it the technical term. And then the curvature k, or kappa. I'm not sure which one off the top of my head, probably kappa. You can't always tell just looking at a book or something. You have to look up if it's officially, because it looks just like K to me. Anyways. But that's the problem with Greek letters. Sometimes it's hard to tell. A few of them look very similar to English letters, at least 1 or 2 of them do. Like especially this one. But besides the point, it's 1 divided by magnitude of v times this thing, the magnitude of dt. So it's 1 divided by secant t times 1. Did you see one? So it's 1 divided by secant t, which is equal to cosine t, and then when you simplify it down, so k equals cosine t. That's how you do that type of problem. Okay. So this one is I and j again because it's a plane curve, I guess. So 2t plus 3, 5 minus t squared. Okay. Component. V is equal to 2i because 2t plus 3 derivative is 2. And 2t minus 2t because 5 minus t squared derivative is 0 minus 2t technically, if you want to be 0, because 5 is 0 derivative. So it's negative 2tj. Magnitude of this is not too hard to calculate. It's just 2 square, because we get 4 plus 4t squared and we take the squares of them. Then it's 4 times 1 plus t squared, and you can take that out of the square root to get a simplified form, 2 times square root of 1 plus t squared. And you do division, some basic simplification. Right up to, so 1 divided by 1 plus t squared, the square root of that, I minus t divided by square root of 1 plus t squared j. That's your t. We got it pretty quickly, okay? Not too much crazy. And now Another way of writing that is with in power form, and that's because I want to use this to take the derivative, which I had to put a lot of room into. I used just the power rule here, derivative, taking down the power. This one I used the product rule. Technically you could have also used the quotient rule, but I thought, why not use the product rule for this, since it seems like it wouldn't be too hard. I mean, I think quotient rule would be slightly simpler in most cases, but I think this one, it doesn't make much of a difference. Really somewhat simpler in a lot of cases. But to be honest, I just wanted to use the product rule again for both of them. Well, not both of them, for this one. That one isn't needed. But yeah, basically that's what's happening here. So negative 1/2 times 2t, the derivative of that. So derivative of the inside times the power brought down times this raised to the new power, which is negative 1/2 minus 1. To the power minus 1. And it's minus this whole thing, so derivative of t is 1. That's derivative is 1 plus, no, it's not a derivative, it's just it. Then you add t, its normal form, because this is the function, then t from there. That's the derivative of t. So now you take the derivative of this, which is just like that one. Negative 1/2 times 2t times 1 plus t squared to the negative 3/2 power. In the end, this simplifies further. It gets into this form. That one's pretty obvious. I dropped that down. I try to drop them down to denominator. Since negative exponents aren't really looked highly upon in a lot of math, you usually don't like to leave them in the end. Your end result in that, if you know, because it's very easy to switch it, put it in denominator. But yeah, negative t, because I was divided by that. Almost t squared to the 3/2 power. And this one, subtracting this whole thing for j, but we just multiply by 1 plus t squared to get the same denominator for both these individual parts. You know, you basically get the same denominator and combine them in that, because it's easy to see that you can probably simplify one of these problems a little bit more. So then you have 1 plus t squared minus t squared, so it's just 1 on top on the numerator. So you get that as your derivative of t, respect to little t, your time. But regardless, you get that. And then the magnitude of this, I kind of am trying to simplify it down as much. Point is, you get t squared divided by that to the cubed, these cube things. You can add them together as 1 now. And I write that as 1 power, 1 t, so basically you become just 1 divided by 1 plus t squared, because that's the third power, so you lose a power, you get rid of that, so it's only 1 on top. And this is equal to square root of 1 divided by square root of 1 plus t squared. In the end, it becomes square root of that. It's basically square root of something squared is the same is the original expression, so it's 1 divided by 1 plus t squared. So, now you find n with these two values divided by each other. Basically, it's individual things, and then, oh boy. You basically have to do the multiplication thing when you divide fraction by fraction, especially. You do that. Dividing by a fraction, you multiply to a reciprocal. And it does have some cancellation, somewhat. Basically, this gets to square root in the denominator, and that's the only difference that's happening here, a little difference from that. Because that's 1 plus t squared to the 1 power, the whole thing. That's 3/2 power, so you get rid of it. Get rid of the numerator and subtract from that what it is. So yeah, that's why it's square roots on the bottom again. And now the curvature is just this 2 times square root of 1 plus t squared from here. and times 1, yeah. It's going to be all in the denominator here. It becomes, this is to the 1 power, so it's to the 3/2 power now when you just multiply them together. You multiply two things together, you get the same, you add exponents when you multiply things. This was the same base with different exponents. So it just, and that can be written also, I guess, one of the answers they want maybe might be in the form of that, but this is correct as well, I'm pretty sure it's 3/2 power. 2 times the square root of 1 plus 2 squared, all to the 3rd power, that's same. Yeah. Okay. Now for these last 3 problems, we want to find t, n, and k for the space curves, and that's it. I can just quickly run through these. I don't think you can read it as you want. You can pause it and look at it. Yeah, but you have this position function. You take the derivative of v like before. Oh, and you have to do. We basically, I think, did a very similar function. It's not maybe exact, but very, very similar in the last practice one. But read through it on your own if you need to really need more practice with these. The methods don't really change though. It's just your basic derivative rules used with other types of simplification rules and exponential, any type of rules really that apply to math at this point. But yeah, that's the, sine squared plus cosine squared equals 1 basically is what's used there. And t is the division of it, of course. Of v and magnitude of v. The derivative of this t is just simply put the normal type things at this point. Oh, 0k though. So k is out of the question here. Negative 3/5 sine t because it's 3/5 cosine t. Then it's negative 3/5 cosine t. Negative 3/5 sine t. The magnitude of this, very, very similar, but you distribute out 9/25 because that's what you square both these you get. And it's sine squared t plus cosine squared t, which is 1. So square root of 9 divided by square root of 25, which equals 3/5. So k we find it's equal to 1 divided by 5 times 3/5, so it's 3/25. And n is the division of those things like before. And dt divided by magnitude of dt. And actually simple, it's division by 3/5 in the both. They already have 3/5 in the first, so basically these are gonna nicely cancel. So it's negative sine t I have to cancel out minus cosine t j for n. And that works out fine by me. 11, it's this one, RT equals product rule. I don't even have to spell it out, but that's basically what we're doing. It's e to the t cosine ti plus e to the t sine ti plus 2k. We had one very similar to this, except for I think it was 2t or something k. But we'll do it again. Amelia. Point is that this is going to have a lot of elimination. And to quickly put, I did that minus 2e from do the product of the binomials. In the end, it's very messy. It's a little bit messy, but it's like what you've seen this one before, kind of. You can read through it in detail if you want to for no examples. 2 to the e2t is basically you distribute out what's common and what's left. Yeah. So e to the 2t cosine squared t plus e to the 2t cosine squared t, they combine to 2 times them, plus 2 times the other one, the like term that combines, you add the like terms. And this you can distribute out 2 to the e2t. So it's sine squared t plus cosine squared t. Yeah. So it's 2 times e to the t squared times 1, which is e to the t draws out at just square root of 2, so square root of 2 times et, or et times square root of 2. And you divide by these, you cancel out, because v, yeah, technically in each of these you can factor out e to the t. That's what I did quickly here without showing it too much. So they cancel out, and you have just cosine t minus sine t divided by square root of 2, and sine of t plus cosine of t divided by square root of 2, for I and j. I mean, this is a space. It is a base curve, even though k is not a major component, especially in its derivatives. K becomes irrelevant. But that too. Either way, you have your value of t now. So that being said, the derivative of this is not too hard to figure out. You just take out square root of 2 from both of them, 1 square root of 2 times them. And you have derivative of the sine and cosine functions as we've done before. That's very simple at this point. Really, the biggest challenge at sometimes is just keeping track of your plus and minus signs to make sure when you're doing these derivatives over and over again you don't get confused. What's going on? It's in the magnitude of this. It's messy to show, but it's the same tried and true method. 1 divided by square root of 2 squared is 1 divided by 2. Because you square 1 and square root of 2. You square the numerator and denominator separately, and you get that. One way of doing it, or you can just multiply 1 over square root of 2 times 1 over same thing. But, so you simplified that. Basically, this thing on its own can also be squared, and it kept it sine squared t plus cosine squared t plus 2 sine t cosine t. Then you have the same thing pretty much, but minus 2. Then these all multiply by 1/2. So I distribute out 1/2, okay, from both of these, and just add those all together. And they simplify, and cosine squared sine squared, both of them turn into 1. So it's 1 plus 1 basically times 1/2. So 1/2 times 2, 1 square root of 1 is 1. That's what that is. So once again, I feel like this is somewhat common because they like to do that. I like to make this one value simpler in a lot of examples, apparently. It might be because of all the cosine squared, sine squareds being able to simplify down so simply. You're going to get a relatively simple answer for that. I just like simply today. Just so so curvature is just 1 divided by magnitude of v, basically. This is equal to 1, this thing. So it's 1 divided by square root of 2 et, or 1 divided by et square root of 2, whichever order is technically correct. Both of them are correct. Yeah. And then it's equal, yeah, it's just equal to basically dt because that's 1, it's divided by 1. So, yep, it's that 1 square, yeah, so it's square root of 2, yeah. Just not much to say at this point. And then 13, it's, t is greater than 0. There's some reason for that, but I'm not going to get into that. So t cubed divided by 3i plus t squared divided by 2j. A lot of this seems pretty simple, doesn't it? Derivatives are going to be nice and clean. T squared I plus tj. And isn't that clean? Magnitude. Oh boy. No, but seriously, like, it seems like, oh, this is going to be nice and easy. Yeah, it's not going to be the easiest because of the messy work. Like, there's no cosine or sine functions or anything crazy, so it seemed like it won't be as messy. It's still somewhat. Basically, yeah, so t squared squared is t fourths, t squared is t squared, obviously. You can divide out t squared, distribute it out. So you get t squared times t squared plus 1, and then it's t times the square root of t squared plus 1 for your magnitude. And the division of this is just, yeah, you have the square root in the denominator for both parts, not changed, and it's just t and 1 as the different numerators. But I and j are pretty much identical besides the numerator, in t and I. And then the derivative of the magnitude, no. Let me see here. Yeah, that's not magnitude. I accidentally put those bars, I think, there by accident, so ignore it. You know, there are always going to be issues with stuff, but ignore that. This is just dt dt. There's the magnitude. It's afterward. We have to try and do t dt first. I mean, I could make it one big step, but that'd be even more messy. Trying to make this clear for the viewer. So the derivative, split up I and j here. J, it's just this basically to negative 1/2 power. This is how I did it. We've done that before actually. This one I used the quotient rule. I decided to man up and use the quotient rule for once. So you have to make sure what you subtract in the quotient rule. So the denominator times the derivative of the top minus the top times the derivative of the denominator. That's how you have to do it. And follow the work along. You have your I and j values, keep them separate. Which can now j is t over t squared, plus, negative t technically by shoot out. Just it's negative t divided by t squared plus 1 to 3/4 power. In the end, but what's happening in the I component is more interesting. So it's square root of t squared plus 1 minus this whole thing. So t times 1/2 times 2t times t to squared plus 1 to negative 1/2 power. And you have divided by t squared plus 1. And then, so that simplifies down to negative t squared over square root of t squared plus 1. We give them the same denominator like before in another problem at this point. Then before, we've done all these techniques before and they're being combined in different ways now. Cancel out, so square root of t squared plus 1, you can multiply by square root of t squared plus 1 to get t squared plus 1 divided by square root of t squared plus 1, and you combine these terms and you subtract t squared from that because that's already there. You get what? And this eventually becomes just 1 over it, and that's multiplying the t squared because we're dividing by technically. So they multiply together, those two things. We do division like this. And you get t squared plus 1 to 3/2 power, because 1/2 power times the same base term but to the 1 power. You add them up. And then the magnitude of this is just these things squared. Some of them. And it could go better. Yeah, because t squared plus 1 cubed is the denominator for both stems. They combine and you get 1 plus t squared. We've done a very similar procedure before for this. Square root of 1 divided by square root of 1 plus t squared squared. You get 1 over t squared plus 1 is your dt dt. N is equal to the division of this. And that should be magnitude. I forgot the magnitude here. I changed it places. Dropping bars where they should be, putting them where they shouldn't be. Yeah, 1 divided by t squared plus 1, and for the components, they basically cancel out. You do the multiplication. And you'll get 1 divided by square root of t squared plus 1i minus t divided by square root of t squared plus 1j. And the curvature is the 1 divided by magnitude of v times that magnitude of dt dt. So it's 1 divided by t times t squared plus 1 to the 3/2 power. And that's it. I don't think these need you just need to understand how to use these formulas for 1 or 2 problems, basically for a couple. Yeah, and if you basically know your derivatives, and you can see it after 1 or 2 of the problems how these work. You don't need to go nuts.